That was really, really loud in my headphones. Okay, so there was one last thing I wanted to talk about the other day that we didn't quite get to. Kind of ran a little short on time, and it had to do with our logical operators. We saw very quickly at the end for our three basic ones, and, or, and not, we can just write out the words. But, well, we're completely missing the XOR operation that way. And something that doesn't really show up a whole lot at this level, but I thought it should be included just to make the complete list, is shifting bits. So for that, we'll need to look at our bitwise operations. Bitwise logical operations. So we're familiar, everybody's seen the logical operations, and or, and not, with two inputs, and I'll set up a truth table. So if we want to look at an AND case, well, we could have two potential inputs. It's a binary value. I'll call them A and B. And we'll combine them with an AND and get some sort of output. So if A is off and B is also off, put those together, we get it off. And is inclusive, so if A is off and B is on, well, they're not both on, so the result would be off. And vice versa, if A is on and B is off, the result of combining them with a inclusive AND operation would be off. Whoops, not a zero there. But if A is on and B is on, so if both of them are on, our inclusive AND operation would have that on. And we have the same thing for OR, which is kind of the non-inclusive version. We have two inputs, combine them with an OR to get an output. So they could either be off or on for each input. And with an OR, if either one is on, our result will be on. Or we could say, use the words true and false. If either of our inputs are true, the output will be true with an OR. I should write a 1 there for consistency. So all three of these would be on, and the output would be, if neither one's on, obviously the output's still going to be off. And then our other basic operation, not, that only takes in one input. It's a unitary operation, so it can either be true or false, and the output is just the opposite of what it was. If it was off, the output not off is on, and not on is off. Those are our three basic ones that we use to do most of our logical operations for combining different conditions and make more interesting conditions to check in selection structures like we were looking at the other day. And in Python, all three of these, we can just spell out, it will recognize the word. But we have some other ones, in particular XOR, exclusive OR, which is just like an OR, only it's exclusive different values. So if A is off and B is on, XOR would still be on, and vice versa. But if they're both on, it's not exclusively OR. So both on would result in an off if we had XOR. And the only way we can get that with Python is with our bitwise operations, which also give us a convenient way to use symbols rather than spelling out the words every time. Because in most programming languages, we use symbols for our and or and not, rather than typing out the words every time. And typically, and is represented with ampersands. Across the board in programming language, our regular and is going to be 2 ampersands, and then a bitwise and, which we'll talk about what bitwise is here in just a moment, is represented with 1 ampersand. So it gives us a way to represent and with one single symbol rather than spelling out the word every time. And the pipe symbol is the typical one to represent OR. It works in lots of programming languages. Kind of the standard is our normal OR logical operation will have two pipe symbols. That's the thing on the key right above the inner key. So the symbol on the same key as the backslash, the little vertical bar. It's called pipe symbol. And not, well, we use different, it's different. That one varies language to language. But in Python, we'll use a tilde to represent the bitwise not. And for XOR, we'll use the caret symbol, which sometimes in reference material, you may see the caret used as an exponent. And it's actually just a byproduct, a result of doing XOR on binary numbers. We get the exponent. But that only works in binary, it's a special case. So we do have, for exponents, we should be using two asterisks together to get the exponent. But it just so happens if we're working with binary numbers and do XOR on the two numbers, we get the exponent of it. But that's just a unique pattern that happens to work out with binary. And I'll come back and talk about the last two operations. So I'm going to go ahead and erase these logic gates. I'm under our truth tables. There's Tom. Hello, Tom. So we were just getting started with what we ran out of time for the other day. A reminder about truth tables and our basic logical operators, which in Python we can spell out. We can spell out and, or, and not, and then make the big comparisons, which we're going to look at an example here in just a moment. But if we want to use symbols, we need to use the bitwise logical operators. And bitwise logic is a little bit different because it will compare bit for bit, just like the name implies. So if we have two binary numbers, 10101, I'll just make a couple up here, and 00110, we have two things we want to compare with an and. Well, if we wrote the word and, this would result in a value of 1 for true because both of them are non-zero. So we have two non-zero things, we put that as and that's going to, like both of them are on, so if we say and, we'll get a value of 1. But when we do our bitwise operation, instead of returning one single bit, like we see with that, with our basic logical operators, it'll return the same number of bits we put in. So here we have 5 bits going in. So with the bitwise and, our result is the and on each one of these columns, and we'll get 5 bits back. So 1 and 0 will be 0, 0 and 1, 0. This third column, both of them are on, so that's going to return a 1. 0 also obviously going to stay off, and they're not both on, so the result of that with and would be off. So bitwise goes bit for bit, and that'll make a difference when we start looking at how to use this. Same thing with OR. If we feed in 32 bits, we're going to get back 32 bits. When we do bitwise operations, we get back the same number of bits we put in. Not would obviously just go through and negate every one of those bits. Everything that's a 1 becomes a 0. Everything that's a 0 becomes a 1. And exclusive ORs, like we would normally use XOR, where one or the other, but not both, is the exclusive OR operation. And with bitwise operations, we're not going to use it much in this class, but I did want to go ahead and mention it. Okay. Thank you, Tom. And yeah, as always, the video lectures are being recorded. So if things happen, yeah, the recording will be posted after very shortly after we finish tonight. It usually takes about 10 minutes before they send me the first email with the link in it. So with the Bitwise operations, we're not going to use this one much in class, but I did want to point it out because I think security people and network people will need to use this one occasionally. And these are our shift operators. And that moves all of our bits left or right. So I'll set up some sort of an example, 11001101. So we have 1 byte here, and the shift operator, the arrows point the way we're moving our bits. So we'll shift left by maybe 3 bits, 0, 1, 0. And when we do this, all of our original 8 bits move 1 spot to the left. And yeah, well, if we're working in bytes, 8 bits at a time, that means we have 8-bit registers going on. So we take 8-bit chunks. So these first 3 are just going to be kind of discarded, and all of these move over enough to fit these bits in. That's one of our Bitwise operators. It's not really going to show up in this class, but I did want to mention it because we have some network people in here, and that is something that will apply in network addressing and things occasionally.
How would that?
Not you. What's that?
How would that be useful for network or security people?
Shifting your sections over. So like on your addresses and things, when you're masking them, one of the ways to do the subnetting is when you write code to do the subnetting, you would just shift the bits over and set it up that way. It's not something that's going to show up a lot, but occasionally if you're working in binary, and remember when we work in working in hexadecimal, we're working in binary 4 bits at a time. We might, if we're working directly in binary, we might have to move our bits back and forth, such as changing the network and domain on an IP address, shifting those back and forward to adjust addressing or other things that you might want to automate instead of going to every single device on your network and retyping the machine. It's just be one bit over. So you just, or the next one in order, so you could just shift those bits into the address and do automate the setup a little quicker. But I just wanted to mention it. So if you see it somewhere, really that's what I was mentioning it for, so that if you see that somewhere, you'll know what that's doing. That operation just takes whatever bits we have and moves them over and throws some other ones in their spot. I don't know how much it would show up with networking because you're usually going to be working with finished machines. One thing that I end up working with a lot with little, one of my favorite hobbies for the evenings is trying to create and invent like new input devices for machines. I really enjoy doing that. Just let the creativity flow and put stuff together. And one thing that often shows up for me is working with things compatible with our Arduinos are going to run the C++ language, which means they're going to try to have 10-bit integers. But when I'm putting that on the machine, I have 8-bit registers. So the size of the integer I have is larger than will fit in a register. So I have to put 2 registers together in order to hold the integers that I'm passing it. Does that make sense?
Yeah, so you'd kind of shift the 10 bits onto two bytes.
Yeah. Yes. So like I'm just make up some here. So we have 8-bit register 10010011, but a 10-bit integer, maybe I have another 01 over here. So that's not quite going to fit. But if I try to move that to the next register, it's going to be over there at the least significant position. So then I'd have to shift it over the other 6 bits. In order to use just those first 2 spots in the register so they line up with that instead of the last 2. So that's something that shows up a lot when putting devices together. But in like your networking career, you're going to be working with machines that have already been built and exist. So I don't know if you would have to go in and use that particular thing. I was just thinking it's something that might show up, and that way you'll know when you see those symbols, you'll know what that means. If you see it anywhere, that just means we're shifting our bits back and forth. These other ones, we will use a lot. And there's one key point, the bitwise point is important to take note of. I'm going to share my screen and just those 2 examples in idle to show how this is applying. So I start up idle here. Yeah, and typically, other than a personal preference for using the symbols rather than the words when I'm writing programs, in all the languages I know, this is the only time I ever use bitwise operators is in Python, just so I can use the symbols, except for the shift operator. That's the only one that shows up regularly. Everything else, I always mention it when I'm talking about programming languages, because it is bitwise stuff is included in every single programming language, but I've never really used it except for so that I can use the symbols in Python or for shifting bits. So it doesn't necessarily show up a whole lot, but I always try to mention it. And yeah, instead of our normal AND, which would return only a single bit, the bitwise AND will return as many bits as we pass in, and just do AND bit by bit. So I'm going to throw a couple numbers here in Python, say 5 and 7, just something to work with. I'll store them in some variables so we can work with them. And then like we saw the other day when we were looking at selection structures, we can combine the way we'll make comparisons. So like x greater than 10 should be false, right?
Yeah. Mm-hmm.
X bigger than 10, x is 5. So if we just type it right in the shell here, we can see what the result is. And that's a very useful thing when putting scripts together in Python, because remember, it's an interpreted language, which means it runs one line at a time. So we can test each thing one line at a time and see exactly what it's doing. But we can put some of our conditions together. So like x bigger than 10 and y smaller than 10. So this first part's false. The second part will be true. So on and, false and true would return a false. But if I scroll up there and just change that and to an or, if it's or, if either one's true, it's going to be true. Then, let's see what, I guess I could do something with not. So like not, and usually if we're doing not, it's a good idea to wrap it in parentheses. Not x bigger than 10 and y smaller than 10. So we know this one's false. And from looking at the values, we know that 7 is going to be smaller than 10. So this one's true. So not false and true would return true. That should be fairly straightforward. But when we get to the other one, so let's say x less than 10, that's going to be true. Y bigger than 5, that will also return true. So if we try to combine those with the bitwise operation, so we can do symbols, so like x less than 10 and y bigger than 5. What should the result of that be? You think that one's going to be true or false?
I don't know.
Yeah, it can be a little confusing. So that one came out as false. Both of those halves were true, right? But when we took them one bit at a time, we didn't get all one. We didn't get all truths. But if I type that in the other way, y bigger than 5 and x and 10 greater than x, y greater than 5 and x. Okay, so that's the same condition in all three of those, right? X smaller than 10 and y bigger than 5, and it gave false. Turned around, y bigger than 5 and x greater than 10 came back as false. Y greater than 5 and x less than 10 gave true though, which seems a little odd that we're going to get different results by putting the same thing in different, the order we put it in matters. So if you want to use the symbols and kind of abbreviate the code that way, or if you need to work with the bitwise operators, it is always a good idea to wrap them in parentheses, like x less than 10 and y greater than 5. This way, it'll follow that order of operations and do the grouping first. X less than 10, that will be true, so it will store a 1-bit value for true. And same thing with y greater than 5, it's true, so it'll store the 1-bit value for that. And then it just compares those 1-bit values. So anytime you're working, the point there is anytime you're working with bitwise stuff, make sure you use parentheses extensively. Parentheses are your friend. Otherwise, you will get different values depending on the order in which you put them in. And just to show the XOR, I didn't write a logic gate or anything up here. Let's say x less than 10, that's true. Then bitwise or y less than 5, that one's less than 6. That one's false. So true XOR false would be true. And obviously, if we flip that around and did false XOR true, that would be true. So I'm jump to the last one and put both of them true. X less than 10 exclusive or y bigger than 5. Those are both true. So it's not exclusively or. It's not exclusively one or the other. That logic operation can be incredibly useful. And some people see it in the SDEV 120 class and some people don't. So I wanted to make sure and mention that in case you didn't see it in the previous class. It is kind of one of our basic operations. But the main point of all that is we can use the symbols, which can make it a little bit easier to work with, especially if you're used to other languages that use the symbols exclusively instead of spelling things out. That's why I always use the symbols. But if you can do that in Python, make sure to wrap it in parentheses. And that's just for building up conditions so we can make complex comparisons. I'll throw one more in here to do still kind of a basic one, but we can combine lots of things. So we know if x is less than 10 and y is bigger than 3, or z is equal to 8, and let's say not y bigger than 2. Just some sort of big complicated condition of a lot of things we might want to check. That goes all the curly braces. You can see our end result, it evaluates back to a single thing. So as programmers get bigger and bigger and bigger, or when you're out in the working field, there's going to be a lot of things you want to check in your scripts. So those conditions will get very large. Just remember, parentheses are your friend. If you don't need the parentheses, it won't hurt anything, just like in math class. And if you do need them, it will make a huge example. So that was just what we ran out of time for the other day, kind of. It's okay if I go ahead and erase the board, move on to tonight's stuff.
Yeah.
So tonight, next thing on the list is repetition. Sometimes we just need to do things over and over and over again, right? It'll be very similar code. We could type out every single line and just change it slightly ourselves. But if there's only slight variances, it works a whole lot better if we can just have the computer repeat with those variances involved. And well, overall, I'll say this now, overall, I'm really happy with the textbook that's used in this class, but there are a couple little points here and there that I'm not so happy with, and 2 of them show up in this section. One of those being, we're working with machines, and in order to do repetition on the machine itself, we're very restricted to what we can work with. Really, the machine itself can only work with feedback, which you're probably familiar with from audio feedback. Right? Somebody like sings into a microphone, goes down a cable, gets amplified, and the sound comes out louder. And if things are positioned in a certain order, that louder sound goes right back into the microphone, down the line, gets amplified, comes back out louder. And before long, the room's just filled with annoying audio feedback. That's where most people are familiar with that term from. Just kind of, it's an annoyance. Though some musicians started using that as just another note their instrument played. They were actually controlling it. And that's what we get when, that's what happens. That's what we can always do with the machine. The basic idea is we have some sort of input. We'll do a bunch of stuff, then get down to some sort of output. And an option we have is we can always take our output and send it right back to the input. That's called feedback. And we can control that. When we take control of it, we can use that as a tool and make things happen. It's what the machine does naturally, so it's very, very quick. It's rapid. When we control that precisely and use that in programming, we call it recursion. But in order to use it in programming, we have to have functions, and that's one thing. Our textbook shows loops before it shows functions, so we can't really go too deeply into that. But when we look at functions next week, we'll take a couple minutes and very quickly look at recursion, because it's natural to machines, so it's faster. And it's been mentioned before, Python is a very inefficient language. So anytime we can do something that will be faster and buy back some of the speed we lose in exchange for all those advantages that make Python really super easy to work with, it's nice to buy back that speed when we can. So we'll look at recursion a little bit before long, but recursion is really hard to work with. When we look at it quickly next week, there'll be a list of requirements that we have to do, and no matter what problem we're trying to solve, we have to bend and stretch it until it fits our list of requirements for recursion, and that can be hard. So to make it easier to program repetitiveness into our structures, most programming languages include loops, which is something specific to the language, already built in that does the repetition based off logical conditions like we saw with our selection structures. Base repetitive, chunks of code, off logical conditions. So just like we saw with our selection structures, we can set up some sort of condition that will give us a true or false value. And then we can just decide to repeat or not based on whether that value is true or false. It's a whole lot easier to work with because it's, again, like we saw the other day, we're just asking a yes or no question that the computer can answer for us. And you would have seen these some in the SDEV 120 class, so quite a bit. Talking about recursion. So there are two main types that we'll use here in Python, and this is general to most of our languages. There's these two types of languages, loops that we'll look at. In your SDEV 120 class, you would have talked about pre-test and post-test loops when we do our testing. But another thing we need to check is there's subcategories of those that we can split up into either a while loop or a for loop. And they're used differently. Typically, they are completely interchangeable. Anything we can do with a while loop, we can also do with a for loop. Anything we can do with a for loop, we also do with a while loop. To some extent, it just takes adjusting the syntax a little bit. But our general rule of thumb for when to use which kind is a while loop is for when we do not know how many times it will run. Do not know in advance how many times. So that's for situations where it might run 1,000 times. It might need to loop through 1,000 times. It might not loop through at all. If we don't know in advance how many times the loop is going to run, typically we'll use a for loop. Sorry, typically we'll use a while loop, and our for loop is the opposite. That's for when we know how many times it will run. And then there's a slight issue I want to be very clear about here with for loops. Our textbook does something that seems really, really odd to me. This is the other thing that shows up tonight that I'm not very happy with in the textbook. And they use numbers in for loops, which I feel like there's some drawbacks to that. It might just be because I learned Python before those numbers were available like the book does, so it seems odd. But typically, know how many times it will run doesn't mean we're going to say it's going to run 7 times. It does. We don't know, like the programmer, when we put that together, we can't say how much it's going to run, but the computer will know how many times it's going to run in advance. Whereas a while loop, it's the computer that does not know in advance how many times it's going to run. And it doesn't really have to do with numbers. There's 2 terms we use for it. It's called iterable or countable. Whoops, that's not how to spell countable. Which the countable one doesn't help with the point of not using numbers. But iterable, what that really means is there is a definite starting point and it will progress, and then there's a definite ending point. So that's what's really meant but I know how many times it's going to run. Typically for a list, we'll have a list of numbers, or we'll have a list of things, and then the for loop is just going to start at the first element in that list and run through every element in that list until it hits the end. Does that make sense? And it doesn't have to be numbers. There might not be any numbers associated with it. So tonight's examples, I'm not going to use the for loop much. The book has some excellent examples. I just wanted to clarify the point about the numbers, because really what that book's doing, it writes something like this. I'm going to erase this little thing I drew here. It'll say like for X in range 0 to 10 or something. And then it'll have all the stuff to go through. And this one right here, range 0 to 10, what that actually does is create an array and put all of our numbers from 0 to 10 in it. So then that's what for loops are really for. We have this array, and in an array, there is a definite starting element, first element, and a definite last element. So it's an iterable object. We can start at the beginning and walk through to the end. And that's where countable comes in. We don't actually count it. We don't go through and say 1, 2, 3, 4. Countable means we could if we wanted to. We could count how many are there because there is a definite start and end. I just kind of wanted to express that point. Whichever way you want to write your homework assignments this week is fine. I would recommend using the while loop if you're going to go further in programming, especially if you want to do a lot more with Python. The for loops, we'll look at them, I think it's next week. We'll see them when we get to a file, reading files. That's another one. So an iterable thing. We have this like a text file with a bunch of lines of text in it. And we don't necessarily need to give each one of those lines a number, 0, 1, 2, 3, or whatever. Iterable or countable simply means there's definitely a starting point and definitely an ending point. So in our for loop, the book keeps using this one, but we could just say for X in file. And in that case, X refers to that line of the file. So it's going to do that for every line of the file, a definite start to a definite end. And especially for those going further, everything we do in this class, it'll be fine to do it like the book does. That range feature is useful. I think it throws me off because I was using Python for years and years and years before they created it, or before that got added to the language. But if you're going further, you want to be careful not to associate numbers with a for loop. There's some important stuff coming later for those going further, in particular comprehensions. I feel like when you're ready to get to do comprehensions, which is far beyond the scope of this class, having numbers connected to for loops is going to throw you off when you get to that point further down. So if you're going further, I would highly recommend using while loops if you need numbers in the homework assignments for this course. And we'll see the typical use for for loops when we get to files, and then when we get to arrays and lists later. We'll see a better use for them without numbers involved. I guess to expand this point just a little more, it's also an efficiency issue. Like I just said, that thing the book does, if we want to use numbers in a for loop, what we have to do is create an array of numbers. Like 1, 2, 3, 4. And we create this huge array, taking a big chunk of memory to hold each one of our numbers. Whereas in a while loop, we would just have a variable. I'll just call it like counter. And then each time through, we can increment that. So we're storing, so to use a for loop with numbers, we have a huge array, however many numbers we need, 32-bit integers being stored there, plus some extra data because it's Python. So a huge chunk of memory just to have those numbers in order. To do the same thing we could do with one variable and just keep switching out what number's there. We can store a 1 in there and then come back and store a 2 in there and a 3 in there, and we get a lot more efficiency out of that. We're using a lot less of memory and things like that. But again, that's something for way further down the line, because obviously anything we do in this class, we're still a long ways from having to worry about efficiency in our programs. But if you're working in Python, it's something to keep in mind, because Python is a very inefficient language. It's easy to use. It's good for the human, but there's a trade-off for being good for the human. So our while loop, our basic structure, we're getting ready to look at some examples, a couple quick examples and then one big example, is we'll have while, and then we'll have some sort of condition like we were looking at the other day. Followed by a colon. So a whole lot like what the if looked like, right? We had if, condition, and then a colon, and then we would indent our code to run, the code we wanted to run. So same thing for a while loop. It's just a different keyword. Then we put a condition there. We need the colon, and then everything we want to run gets indented at the same level inside of that. And when we're done indenting, we just undo the indenting. Very similar to what we saw with the if block. And our for loop, our general, instead of checking a condition that will eventually become true, for loops are really for iterables. I guess that's why that range function the book likes to use works, because that creates us a list of numbers. We can say range 0 to 10, and then we have an array that just has all the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is an iterable. It has a starting point and an ending point. So our syntax is like for, I'm going to write the word item, and that's a reference name. We make that name up just like a variable name, and then we use it inside of our for loop in iterable. Some sort of structure that we can walk through, a colon at the end, and then once again, we indent our code to run. But as far as the syntax, our book is really, really good at throwing up those examples and showing some of those. Does that make sense? So 2 types of loops. One of them, we check a condition. And then as that loop progresses over and over and over again through every run of it, that thing we're checking is going to change slightly. So we don't know how many times it's going to run. It's just going to run until this condition is no longer true. So as long as this is true, so while true, do the code to run. Oh, which is another thing I should probably put up here. If you do want an infinite loop, typically that's something we want to avoid, right? But there are some situations where we want an infinite loop. The example that I always throw out is like an animation on a website. When people come visit your website, if you have an animated logo, you want that animation to run over and over and over again until they hit the close button on the browser and leave your website. And if that's what you want, if an infinite loop is what you want, just put true for the condition. That way it is completely obvious that you wanted an infinite loop. And you won't ever have, because we could put something that would always be true, right? Like we could put 1 greater than 0. And that's the exact same thing as writing true, but when you see it, you have to stop and think. Or other people might wonder why you did that. So the standard is if an infinite loop is the goal, which it is in certain situations, just write the word true for the condition. That way it's obvious to anybody that looks at it that an infinite loop is the intention there. Have anything else on the notes? Yeah, and we'll see for loops in more detail. The book uses those most of the time, and it uses them with numbers. So there's plenty of examples of that if you would prefer to write your examples that way. For right now, the examples we're looking at, I'm just going to use a while loop, and then we will see for loops with the proper usage starting next week. I think we look at reading files whenever we see reading files. So let's look at a couple of examples of these and see what they look like. Does anybody have any questions about that?
No.
Okay, so I'm going to go ahead and share the screen. And I already have Python, have idle pulled up here, so I'm just going to create a new text file and display the syntax before we get to the big example for tonight. So let's say I'll put some notes in here to jot out a little plan of what's getting ready to come. So an example of a while loop, then example of a for loop. I'll go ahead and do one example of that just to show what it looks like. So just like our if statement, I pointed out a moment ago, we need our keyword, which is going to be while, and then a condition that we want something to happen as long as that's true. And for this, I'll just go ahead and do something 10 times. And with the while loop, we have to take full control of our counter. So like counter, I'll start it off at 0. And then the condition, so while counter is less than 10, and that's going to be something that's going to return true or false. The first time through, counter is 0, so that's true, so it'll do the code in here. Then the next time through, if counter is still less than 10, it's going to keep doing that until counter eventually gets to a number bigger than 10. And then we can do stuff. I'll just print some sentence counter plus times through a while loop. So I'll just print out how many times that's going to happen. And this is the thing I showed the other day. I like to put code together in the order I think about it in. But the order I think about it in isn't always the order the computer needs it in. Like concatenating this together, the first thing I thought of was I need that number, then these words. The computer needs that number to be cast into a string so it can combine it with those words. So often I find myself working sort of inside out. And with a while loop, we do have to watch this, because we do have whatever our condition is, you always want to make sure that changes somewhere in the while, somewhere in the loop. That way the condition will eventually become false and we'll be finished looping. So the typical thing is just to increment our counter. So I'll say counter plus equals 1. So I'm just going to increment it by 1 each time. And then it's going to print so many times through a while loop. In a for loop, I'll do a very similar thing. Well, I guess I'll do the exact same example. So for I'll call it counting in range 0 to 10. I'm going to print whatever value counting is plus times through a for loop, if I can spell it correctly. And again, that counting is a number, so that needs turned into a string whenever it runs. So these are basically going to do the same thing. Let's see, I'm going to add a couple blank lines between them just to tell which one's which. Does that make sense? With what y'all have like seen in the book or your experience in the previous class? So our condition goes first. Like in the SDEV 120 class, working with Raptor and doing the flow chart, the condition ends up in the middle, and then we do stuff either above it or below it. But in both cases, our saying we have a loop and then the condition to check is first. Or the for loop, we have a loop and our iterable is the second. If that makes sense, I'm going to go ahead and save and run this. And it should just print out those lines a few times. Go over here, save and delete folder, loop, for example. Some random name on it. And now I'll hit F5 to run it. And we can see it just kind of goes through there. It does the same thing, goes from 0 to 9 and prints out those words over and over and over again. So if what we need to happen is something that needs done repeatedly, we can use either type of loop and get the same results. The difference, I guess, for those going further, there's an efficiency issue that changes. So our efficiency on the while loop is one int variable is recycled for all the numbers. But on the for loop, an efficiency issue here is that range function creates an array that stores all those numbers, 0, 1, 2, 3, 4, 5, 6, 7, 7, 8, 9. So you can kind of see it wrote out like that, right? Up here we have one integer, and we're just changing what that integer is every time. Whereas on this one, we have this very large block. But otherwise, they can be used the same way, and everything we'll need to do in this class is the same. And either one, whichever one you prefer to use, is fine for the homework. And my only recommendation is for people that are going further in programming, the software developers. If you're going much further in programming, for starting out here, it'd be much better if you have numbers to use a while loop. There's some stuff coming later, not in this class later, but later as you learn more and more and more about programming, in particular comprehensions, that I always worry starting out with numbers in a for loop is going to throw people off when they get to comprehensions, which is a very powerful tool that we tend to use a lot. But any questions about that? That same thing I put in the comments, I'm going to draw a quick picture of for a visual representation of that. Oh, Dustin's here. Sorry, I didn't see you in the waiting room. Had you been there long?
No, just about 10 minutes. So sorry, I just got home from work though.
Okay, I was doing a screen share of quick examples,
Hey,
showing the syntax for a loop, while and for loop. The video will be recorded, so you can check back over those.
Yeah, I'll catch up on it.
So I was just going to draw a picture here showing the difference in efficiency between the two. So our textbooks really like to use numbers in a for loop, and I wanted to make a big deal out of that because typically for loops are for when we don't have numbers, and while loops are for when we have numbers. That's what do not know in advance. We have numbers, so we're going to manipulate those numbers until we get a true condition. Whereas a for loop is for an iterable. That's something that has a definite start and a definite end, like a file. When we read a file, there's a definite first line and a definite last line. So we can iterate through all of those without having any numbers involved, without doing math on the numbers. But in general, if you don't know how many times it's going to run, it depends on the calculations. It's a while loop. And if you know how many times it needs to happen, that's a for loop. So I'm going to write maybe a W. So for the while loop, like we just saw, we can store the number that's going to keep track of our condition, like in that case, we said less than 10. So that counter started at 0 and just walked its way up to 10. And we were able to store that in one variable that was holding integers the whole time. So a little bit bigger than this, but for the sake of the picture, I'm going to draw 8-bit integers. 2, 3, 4. So that's how many bits of memory it would take to do what we just did. Whereas what we just did with the for loop, excuse me, that's going to point to an entire, we need an iterable for a for loop. So that range function creates an array. And in our case, we did the numbers 0 through 10 again. So we had 10 elements. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each one of those elements contained 8 bits. One, 2, 3, 4, 5, 6, 7. So hopefully that picture, you can see why I was making such a big deal out of that. That's our memory usage when we use numbers in a for loop. It's quite a bit different. So Python's not a very efficient language anyway, so it runs a little on the slow side. So using our memory like this, when we could do this, it's going to get even slower. But any questions about that quick pass at the syntax there?
Oh, should be good.
No.
Okay, and since Justin just came in, let me share the screen just to show you. So here's the syntax. Might as well review it one more time because reiteration, the point of tonight, that is a very important aspect of learning, right? We need to hear things a few times and then they stick in our minds. You'll notice the while loop is a lot like the selection structures we did the other day. We have a keyword, then we have a condition that is going to return either true or false, and then we indent all the lines that we want to happen over and over and over again. So it's going to keep repeating that over and over and over again. And when we're done with the section that repeats, we just undo the indenting. Just like we saw with the if structure the other day. It's just our keyword says it's going to happen a whole bunch of times instead of one time. And the syntax for a for loop, the word for, then we need some sort of variable. That way we can refer to what we're looking at over and over and over again, each additional one. In some sort of structure we can iterate through. The book really likes this function for the range of 0 to 10. So all the numbers starting at 0 going to 10. And what we're actually walking through is called iterable, which simply means anything that has a starting point and an ending point. And then once again, just indent the lines we want to run when that happens. But the videos are being recorded, so you can check the recording later. So I'm going to erase the board and get started on this somewhat larger example. Is it okay if I erase everything?
Yep.
And the picture there, that's why I made such a big deal about how the book likes to use numbers in for loops. And you can really see it in the picture, the stack heap diagram. So other than that, the book has some excellent examples of walking through with loops and stuff. So while we're talking about them in class, I wanted to go through a problem solving issue because we've talked about that a lot, solving problems. And our textbook is mostly about the syntax of Python, so it doesn't get into a whole lot of problem solving. You would have seen it in the SDEV 120, but I'm going to walk through what a traditional way of finding pi, I guess. We're going to look at what's called the Monte Carlo simulation. For finding pi. So everybody's familiar with the number pi, right? The thing that has to do with circles. The 3.14 is what most of us have memorized, but the digits go on and on and on. The digits go on forever. And finding the accurate value can be a little tricky. There's a there's a lot of interesting historical notes, long history of tracking it down to the accuracy we know today. And there's different ways that we can check for it. And one of the traditional ones in computer science classes, whoops, I left an N off there. The Monte Carlo simulation. So, has everybody heard Monte Carlo before somewhere? Have you heard of the place?
The car?
Sounds familiar.
It's famous for Monte Carlo casinos, gambling. That's it's a gambling reference. So what we're going to do is use random numbers in a simulation to find pi. Sort of taking the bet that if we look at enough random numbers in a certain pattern, we can find pi. So that's the problem we'll solve. So gamble that if we look at enough random numbers, so that's what simulation means. Just look at enough test cases, run test cases over and over and over and over again. That's why this example is a good one for loops. We just do it over and over and over again, many, many times in some pattern. Can we find pi? Find a reasonable estimate for pi. So instead of find, I'm going to say estimate. Because again, pi is an irrational number. The digits go on forever. We can't find the exact value. But can we get a good estimate from a random simulation? So that's the problem that we're going to look at in an example. What time is it? 7:05. Okay, good. So I can put the first step of this up here to get started before we take a break here in a moment. So what do we need to do in order to do this? If we're thinking about pi, what's the first thing that's going to come to mind? Where do we use this number at?
For a circle?
Yeah. So we know we're going to have some sort of circle. And, for problem solving, we're kind of asking this question. So we can have the computer, this part's easy. So Monte Carlo, like we're going to take a gamble that this will work for us. Then simulation, the computers are great for that. If we look at enough random numbers, so gamble for the Monte Carlo part, look at random numbers, that's what simulation means. Can we find a reasonable estimate about pi? So we might need the things we know about circles. There's a couple things we know. The very definition of pi, right? The pi is the ratio of the diameter to the circumference, which in schools nowadays probably learn that circumference is equal to pi times the diameter. But we could write that also as pi equals circumference C over D. One of the things we know about that. We also have an area enclosed with our circle. Area equals pi times radius squared. And we know similar things about other shapes, right? Like squares, rectangles. So maybe we could do some sort of combination with that and see if we get anything out of it. That way we have some comparisons, right? Because we want this to work for any circle, which means the radius and diameter might be different. Those are also unknowns. And you may recall from a math class, in order to set up and solve for something algebraically, we have to have as many equations as we have unknowns. So we might need some more equations. So maybe we'll need a square or rectangle as well. And for that, we know the distance around as well. We just add them all up. So twice the length plus twice the width will give us a way around all the way around. And our area is length times width. So hopefully we have enough that we can pull the information, all the information we need from. Right? We'll end up with one thing that we might not, that might be a variable in each case. There's like 4 situations. And just listing this out. So going through the problem solving steps, maybe we'll need something else. We also know about triangles, right? Some of our basic shapes. So the perimeter around a triangle, we just add up all the sides. There's not a nice formula for that, but a triangle will only have 3 sides, so it shouldn't be too difficult to add up all our numbers. Actually, there's lots of formulas for that, but there's only 3 numbers, so we'll just go with the add them up formula. And we know the area of a triangle is 1/2 base times height. It's half of a square, so we just label it different, but the bottom times one of the sides is how we would find a square, and a triangle is half a square, so half base times height. So a couple different shapes that we know something about. So can we use these geometry questions to figure out what this value is, or a reasonable estimate for it? And the point of this example isn't going to be to find pi, because in order to check how good our estimate is, we're going to actually ask the Python language for pi. We're going to ask for the 64-bit version of pi that Python knows. That way we can compare our estimates. So our point's not going to be to find pi, but the problem solving, walking through, how can we analyze, break down this problem and figure out an algorithm that will give us this number from just randomly checking things. So let's see, 7:10. So why don't we take a couple minute break and think about that and see if you can start to see any way we can combine the few shapes we know about that we can check random stuff, and we will walk through the simulation itself. This is a very traditional traditional computer science one that shows up in classrooms. So we'll walk through that after a break. It's 10 minutes. Does that sound good?
That's good.
Yeah.
All right. So it's 7:11. So we'll be back here at 7:21, and then we'll go through the Monte Carlo simulation to find pi, and do that in Python. I'll stop the recording and see you all in a couple minutes because I am very